Okay, this is session number 5. We are in the third week of the course on mathematical methods of signal processing. I hope you can see the screen, which shows theorem 7, which is more or less the main goal of this week. We have seen from the cubic polynomials, which are a harmless four-dimensional space of continuous functions. Let me see in chat. Okay, thank you for the comment. I have to share the screen once more. Can you see it now? So the goal is to go from the harmless space of cubic polynomials, which is a space of continuous functions, which is translation invariant. So with every cubic polynomial, also the shifted polynomial is a cubic polynomial. And therefore it makes sense to ask what are the linear mappings, not in full generality, but those who are commuting with translations. And we have studied them and we will discuss them further out. But they are well characterized by certain linear functionals. Okay, so I hope all the others can see the screen. If not, I don't know. Please raise your hand. Okay, now the goal is to do exactly the same thing for the space of continuous function vanishing in infinity. As I was indicating last time already, for practical situations, if you want to test a signal, I think you will always have only the chance to have an input of finite duration. And you will watch for it for a long time, perhaps, but not forever. So, for example, think of seismic exploration. People are having these vibrating trucks. They vibrate, and there is a reflection, and after a while, in a big area, they are measuring all their system responses. But of course, they are measuring a couple of seconds after the vibration until all the reflections that are not too much attenuated are observed. And what we are trying to understand is what is, assuming linearity, going on between the input to the vibrations on the Earth's surface, going down to the Earth, reflected, coming back, and observing. And we assume that we are interested in the part which can be captured to an arbitrary percentage if you would be able to observe for many signals and for many long enough output vibrations with high precision to really understand the full system, and then in order to analyze it and so on. So just to give you a glimpse on what is the end of this week, hopefully, is we have exactly the same situation. We will call it a bounded measure, which are the functionals. We will discuss them in great detail. And we will define a convolution operator. And you'll see formula 66 on the screen, which shows that, well, given a measure, so if you have a functional, the convolution operator m of f, at any point x, we are used to put variables x, so in the polynomial example it was y, and you just do more or less the same that we have done with the moving average procedure in the cubic polynomials, meaning that we are applying the functional to the shifted version of the flipped function. So f flipped is the flip version. This flip operator is important, as we will see, in order to be consistent with the tradition of convolution operators, but it's not really changing the philosophy, and we get the same convolution that we had before. On the other hand, of course, you can ask, well, I have a system, how can I find the generating function, the functional, or you would call it an impulse response? So how can you find the impulse response once you are given the system? And then my recommendation is, well, the impulse response is a linear functional. You have to know how to apply it to a test function, to a C0 function. So the trick is just take that test function, flip it, then apply the system, and then evaluate it at 0. Since flip is a linear operation, the channel, the operator T is linear, the evaluation operator is a linear operator. You have a concatenation of linear operators, and so this is clearly a linear functional. The main task, mostly tomorrow, not on Thursday, will be to describe that all the operators obtained in this way are all the translation invariant operators. We can measure the size of an operator by the operator norm. We measure the size of a functional by the functional norm, and there is an isometric mapping. So that's a perfect match, exactly as in the cubic polynomials, except that we have to do more work. Okay, so this is the kind of midterm motivation of what we are going to do, and now I'm returning to the special notes which I prepared on the side. I hope I find, yeah, here it is. So I'm recalling to you what we had already in the last week, namely that we have to look at the connection between a functional sigma. Sometimes I'm writing sigma sub t if it's the linear functional, or the linear functional corresponding to the channel or system capital T. And the key will be, and we will discuss it in the more practical situation. Okay, I have to check. Okay, it seems that there is no problem with the slides. I'm restarting my slides. Well, is it better now? So we have now the situation that there's a one-to-one correspondence, and I thought it's maybe a good idea to go back to this a little bit more precisely in the terms of looking at our concrete assumption model. So last time I was a bit confused because the first column looked a little bit like binomial coefficients, so I thought there was a mistake. I have checked everything now. These notes were correct. So there was this system, this mapping which maps the polynomial to something which combines shifted derivatives and so on. And the resulting matrix is here visible as number 28. So the question is, how do you get such a matrix? And then you have to recall general linear algebra effect. If somebody is giving you a basis, in our case it's the polynomial basis, the monomial basis, sorry, consisting of x third power square x and constant 1, which is x to the power 0, of course, because this is in MATLAB order. And then you insert into your system the cubic polynomial, the square, and so on, and you write the output by the in the coordinate system. So if I insert x to the third into our concrete operation, I don't do this in detail, I will get x third power 3x squared minus 3x minus 1. So this is the output of the first monomial, the second, the third, and so on. Now, on the other hand, there was this procedure where you are asking what is the value of each of these polynomials if you apply the functional. I was giving you the procedure, and the procedure was very clear. Take the thing and take the value at take the value at 0. Now, we don't have to do very much now anymore, because if somebody is asking you, I have a polynomial, let's say the first one, the output of x to the third. It's another polynomial q of y. And what is the value at 0? It's clearly just the constant, because all the x to the k with k larger than 1 are vanishing, so it's just a constant term. So it's very easy to describe the linear functional, which I described as sigma, by a scalar product with some row vector. Recall on this kind of sometimes stupid statement that the dual space of R4 is R4, the dual space of column vectors is row vectors, but it simply means every sigma applied to a polynomial which is described by coefficients A. So you see I put A1 is the first coefficient going with the first exponent, which is cubic here. So it's this MATLAB order. And so the answer is, I will get, if I try to look at the answers, is the scalar product of these coefficients. And so the scalar product with B is, of course, minus the first, minus the second, plus 1 times A. So it's very simple. So if you look at this situation from this point of view, what the claim of the abstract situation was in the last course is, if somebody is giving you the T, you can find the sigma or the row vector B. In this case, just throw away everything, take out the last row. And the claim, the interesting claim is, if somebody only gives you the linear functional, you can recover the system. So what you are doing is take your input polynomial, shift it. Well, you have to apply the shift operator to the coefficients to get the coefficients of the shifted polynomials first, and then take the scalar product of this. Still, you would like to know how to get from this row vector the full matrix. So how get the upper part? And the claim of the previous course was, if you know the matrix represents a translation invariant operator on the cubic polynomials, then there is a unique way of expanding the row vector to a 4x4 matrix. I would like to leave this as an exercise and or as a challenge if you want. It's not completely trivial. And if somebody has an idea, you don't have to provide a complete solution, but if somebody has an idea, I think it would be good that you're reflecting it yourself or writing it to me, and before working it out, maybe we put this also in the database of our course. Otherwise, of course, later on, but not too early, I will show you how to do it or give more hints. Okay, so this was the situation with the polynomials. Now I'm trying to stop the screen and start with a new one, which is the course material. No, that was wrong. I should have gone back. Yeah, just have to go through this. So from what I have said so far, it's clear we have to study in more detail the linear functionals, and recall that we have in mind to study Bibot systems, so operators from C0 to C0. The reasoning why I don't take the bounded continuous functions here as input, respectively output, will become clear during the course. So the first topic I would like to discuss in more detail is the question of what are typical linear functionals. So the first thing I'm showing you is a representation of a discrete, finite discrete signal. So I'm using the stem function. I just was using an arbitrary grid. So you see I'm taking signals of length 480. Later we will use it as a periodic signal, periodic discrete signal. And then I took a sampling distance of 10. So I was placing random values between -1/2 and +1/2. So the range of the values is 1, but it's symmetrically arranged around 0. I think that's better than only taking positive band values. And then I was saying, well, if you take the height of this needle as the coefficient CK, it should be CK here, I have to correct it, and it should be delta XK. So I have a sum of Dirac measures with some coefficients. So I have 60 coefficients made up in a distance of 10, no, 60, probably 48, because single length is 480. Okay, and then the question is, why is this a bounded linear functional? Of course, in the finite dimensional setting, it's clear, but how can we determine the functional norm? So remember, if somebody is giving you a linear functional, it's a thing which maps signals into the real or complex numbers. And then the question is, what is the size of such a linear functional? And the answer is, well, just put arbitrary functions in C0 with a maximal size, so supernorm, infinity norm equal to 1, and see how big you can get. So how big can you make it? And then you ask for the sup, which is the least bound that you can use for all these things. And the claim is this is exactly the sum of the coefficients. So you could say Ck is the mass, positive or negative, or the load. Then you take the total, absolute total of the masses, or the sum of the absolute masses, maybe it's the better expression, of all these discrete measures. And I will try to explain this to you why it is working. I mean, in practice, this is the right number is easy to compute, whereas the left you have the operator norm, the functional norm would require to have a huge amount of test functions, and the random testing, that might be another example, probably will not bring you close to this. Now I will use the figures later, but oh no, I see, no. I didn't do the details, but so I have to talk here. So what we have seen already is if you take the norm, I will maybe put it in the notes in more detail. If you take an individual delta, then of course the norm of a delta function is just 1. Because if somebody samples a function at a given point, by the definition, the value at the point in terms of absolute values is at most the maximum size of the function, and therefore you can always estimate absolute value of f of x, which is delta x at f, by the supernorm. So the constant 1 for an individual delta is fine. Now here you have a sum of a linear combination of Dirac measures, and because the functional norm is a norm, you can apply the triangular inequality. The sum of the Dirac measures with coefficients, a linear combination, has a size which is at most the size of the individual measures, and Ck times delta xk, the correct reading of the left-hand side, will be exactly Ck. So this is the inequality. Less than this is just the triangle inequality plus the information, what you know about Dirac measures. On the other hand, now the question is, well, maybe somebody is smart enough to find a constant which is smaller than this constant. So maybe this is not the best constant. So we will do it in another example with continuous densities. I've written it down in more detail. But so the question is, how can you make the action of a linear functional as big as possible? And now if you just take constant 1, for example, in this case, a plateau function which is constant over all these values, what is the action that you get? You get the sum of the coefficients. So great if the coefficients are all 1. So I would say, remark, if all the coefficients are positive, that's very easy. So you just take any function which has constant value at all those finitely many points and then goes down. So choose a smooth or some plateau function. That's very easy. However, what are you doing? And now look at this picture. If you have a function, if you have values which are negative and positive, and then the rule would be try to make a function which has maximal size only 1. So you see the blue curve is now the f which is in the pool of functions that we can use for test functions. It doesn't exceed the absolute value plus or minus 1, and it maximizes the impact. Now, what I can show you here, why is this a good idea? I can show you because if you look at the effect now, I have more or less plotted one more thing. I have multiplied my collection of red dots with this blue function. So at every point, which was a red position, I was multiplying with the value of the blue curve. And what you see is more or less the red points which have represented positive values, they disappeared, which means there has been no change. Maybe in this area before 200 at 180, take one of these values, but there was maybe one of the maximal values, it was plus 1/2, multiplied with constant 1 is doing this. So the black one is overwriting the red one, which was at the position, and I don't see even any change. On the other hand, if you look at the red positions below the zero level, you see they are reflected. So it's clearly from a negative value, you get a positive value, which is exactly what you do when you go from ck negative to absolute value of ck. So multiplying a function or a discrete measure or multiplying the amplitudes with some function which has the right signature at the positive and negative values is giving you maximal input. And now think of what you're getting when you're taking the sum of the values f of k with this discrete measure. Then at each position where you have now a black point, what you're getting is an amplitude. The phase is coming from the function, so at the places where the coefficient was negative, it was taken as a minus because the function value was -1. So you have f of xk times ck, and that was always by the construction of the function absolute value of ck, and that's exactly what we were claiming. So it's clear that by the triangle inequality you have an estimate to the lower, and on the other hand there exists some function, because I mean finitely many points are always separated, and we take the canonical representation. So nobody would take, let's say, 2 delta at one position minus 1 delta at the same position. You would say 2 minus 1 is just 1 positive unit here. So you are writing the canonical representation, then you look at the sign of the corresponding coefficients, then draw a continuous function which doesn't exceed 1 and +1 and -1 with the right sign at those points, and then you get that this is the best possible bound, because if one such function is giving the right-hand side as a bound, then there cannot be a lower bound which is smaller. So we are done with this case, and I would call these the simple linear functionals. They will be very important, and they will be used to approximate the continuous one. That's the task ahead of us. And also we will see that it's allowing us to transfer ideas that you have from discrete signal processing to continuous signal processing. So that's actually one of the main tasks that we have ahead. Now, the next topic I want to raise or discuss is the continuous case. So what if you have a measure which is arising by integration of your input function f of x against some decent function? We could do it now with Lebesgue integration, and we would talk about the space L1 of absolutely integrable functions, or more correctly about the equivalence classes of measurable functions which are integrable in the sense of Lebesgue. So whoever has taken a course in measure theory would know what I mean. For all the others, the point is we don't need to have this fancy integration theory, which of course was very basic for the development of functional analysis, but we just take the harmless nice functions that we know already, the continuous functions which compact support. So if I'm taking a continuous function f multiplied with another continuous function with compact support, the product will vanish outside of a ball of radius r. So it's a Riemann integrable function, so you can take this as a multi-iterated Riemann integral. But of course, for illustration, I will draw pictures for the one-dimensional case. That's one of the tricks of people in mathematics, to use symbols which are reaching very far, explain the details of what the meaning is, and then illustrate it by harmless 1- or 2-dimensional images. Now here again there's a typo. It should be the measure induced by the density k of x. So the measure is a functional, and there is a new claim now that this is, first of all, is a linear functional, a bounded linear functional, a continuous linear functional, and secondly, it has a size, and the size can be determined directly from the density k of x, and it's just the integral, and that's what we call the L1 norm. Maybe one should also illustrate, of course, this here. This term is just the area between the graph and of the absolute value and the x, the 0 axis. Or if you just plot the function, you just fill the area between the graph, positive and negative, and take the area without sign. And so a function has a big L1 norm if the area under the graph is big, and it's a small norm if the area is small. So if you think of approximation in the L1 norm, you will see it may happen that you have big deviations at some points, but then they have to be very small. So you can, well, maybe take other examples. So it's really a norm. So the sum, the L1 norm of a sum is less than the sum of the L1 norms. Clearly, if you rescale a function, let's say by 3k has a graph which is 3 times the amplitude. So you know what happens. It's 3 times the area under the graph. You could try to take the dilation operator and check yourself how things change. We have this in the lecture notes. But let's now try to estimate this norm. First, now here you have the more correct formulation. First, I'm saying, well, is it in fact a real functional? So is it possible to estimate the measure norm? So I'm using M or MB. We will not use unbounded measures very much at the beginning. So can you measure the functional norm by the L1 norm of the function? And again, this is determined by the Riemannian integral of absolute value of k. And I will use the plots only later, but discuss it here. So what is the task? We have to estimate the size of the linear functional in terms of absolute values. So we write it out. There's a bar missing, okay. And then it's an easy and harmless fact that if you take the value, the absolute value of an integral, it's at most the integral of the absolute values. That's quite clear, because if you have functions which are positive and negative, you increase the estimate. If you have constant sign, either positive or negative, then it's exact equality, so it's no problem. Now, what do we know about the f? Actually, very little. We know it's bounded, and there is some number, and we take the best possible estimate for the size of the function, which is, by definition, the subnorm of f. Now, if we estimate this f of x absolute value by the subnorm, it's a constant, and we pull out the constant from the integral. The remaining term is integral absolute k of x, which is the L1 norm. So yes, this is obviously a linear functional, and it can be estimated, so it's bounded. And if somebody asks what is the one possible estimate, so this estimate shows that the functional norm of mu sub k is clearly controlled by the L1 norm of the k. Now we have to show, exactly in the spirit of the previous one, that there is no better bound. So if somebody would say, well, maybe I can find an upper bound for all these integrals, which is a little bit less. So the L1 norm of k minus some positive epsilon. So in order to exclude this, we have to show, well, if you would try such a better estimate, you would fail, which means you would find some f in the repertoire, which is a function with subnorm 1, such that the absolute value of this functional induced by the density k would be bigger. So again, the absolute value is missing, but I will correct it. And now I'm coming to the plots. I'm not giving all the details, but giving more the intuition and rather explain the plots in more detail, because the rest you can do. We have seen from the previous example with the discrete measures that you have to turn negative values into positive values. So think now, in this case, the k of x would be the blue thing. And you would say, well, there is a very easy function which turns negative values into positive values, which is the signature. And actually, I was doing it with the sign command in MATLAB. So I was actually, later on, you will know it, I produced a periodic function, it's okay, a trigonometric polynomial, by randomly choosing Fourier coefficients, turning into something real, which is then positive and negative. And the red curve is describing the signum function of this curve. So clearly that is not bigger, but it's not continuous. And because of my approach, I should have a continuous function. Now, there are two ways out of this. So in integration theory, you would say, never mind, this is still an L infinity function. The product is still a measurable function, and therefore you are getting something like this. But I have preferred to stay with the continuous setting also because it's more general and it can be applied to more general situations. So we have to look at this picture. So what I actually did was some smoothing of the red curve. And you see two different versions of the smoothing. The first one was the green one, and the second one was the black one. So you could say, the green one is more beautiful, but it's not exactly plus and minus 1, so it's not very close to the red one. Whereas the black one is already closer and will be more suitable. Actually, what I did, I was using my discrete Gauss function, I was compressing it, so I was smoothing it. And the green curve is smoothing with a narrow Gauss function, and the black one is smoothing the red curve with a very, very narrow Gauss function. So in this way, you get a function, and you can imagine that if you take a curve which is like the black one or even closer to it, so very little smoothing, then you are getting something which up to those areas where you are changing the sign, where the smearing is maximal deviating from this, is a problem. So I have to try to have a generic argument. That's why this figure is only an idealization. So here you could say, oh yes, I tried to make the smoothing such that, in some small interval around the zero crossing, I have no change. In my picture, I have only finitely many zero crossings. But if you think of, let's say, a function like cosine of x squared, you might have countably many oscillations on a very long interval. And then this construction would be not so easy. If you then say, well, now I do the same thing with 2 dimensions, you may understand that this argument is not bringing you completely to the target. In the lecture notes, I have a complete proof with some more elegant argument. I must say I was using such an argument as displayed in the picture for some years until I found a more direct argument, but this is more theoretical. So for me, the point is, yes, the black curve is a candidate curve. It's one of the curves which doesn't take values which by absolute value are bigger than 1. So it's allowed to do it. And if I apply it, what I'm getting is almost the area under the positive function. You see here maybe in the lower part, there are areas where the function is negative, and they should be turned positive before doing the integration. And so it's clear that the integral, to go back to this here, the integral mu of k, which is integrating f of x against k of x, k is the blue guy, f is the black guy. The black guy turns the blue into the absolute value of k of x, so you're getting exactly what we have to do is bigger than 1. Okay, so I think this series of plots should tell you that we are in good shape and we can determine the area. And now I have to again switch to the script and start a new part. So recall we are going for this, but now I'm going to the earlier part. Yeah, so now I'm back to the notes, and actually I take the version which is downloadable at the moment, and I will let you know when I'm changing it. So the first observation is going back to this measurement of the size of discrete measures. So you hear it's better. That if you give me two different points, then the size of the difference is always 2, independent of how close they are. Why? Because you have a canonical representation, it's 1 times delta x minus 1 times delta y, or plus bracket minus 1 times delta y. The absolute value of 1 plus the absolute value of minus 1 is clearly 2. So it's because you can find a function, maybe take a triangular function, which is plus 1 here, goes down to minus 1 at y, and goes back to 0, then you see it cannot shrink. But if you use x and y closer and closer to each other, those triangular functions, this piecewise linear function, would have to be steeper and steeper. So we will see that in some sense, if you let points xn goes to x0, maybe you take 1 over n going to 0. And the delta at 1 over n goes to the Dirac, but not in the norm, but in a different way. Namely, in the terms of the action. You could say, okay, the Dirac measure is now for me not a signal, it's a measurement. And so if I have a collection of measurements, a sequence, here a sequence of delta n, I watch what it does whenever I apply it to one of the signals. So f is any bounded continuous, or in our case I would say C0, but even for bounded continuous you would be able to argue delta xn to whatever continuous f you applied, it goes to delta x0 of f. Why? Because you evaluate f at xn, so you have to look what is f of xn, and the limit should be f of x0. But this is actually the continuity, the definition of continuity at the point x0. So for every function f which is continuous at the point x0, this will be true. Now the bounded continuous functions are continuous anywhere, so for any sequence of convergent points you have this relationship, whereas if the points are distinct from the limit point, the distance is going to 0. So this will be a first glimpse into the situation of convergence of discrete measures. Now the next thing before the break is a general statement about the general functional analytic observation. I will give you a concrete example. So we have seen that the finite discrete measures are very nice and easy to look at. Now the question is, now I'm using a topological argument. If somebody is giving you the open circle in the plane, and you're asking, what is the closure of the open circle? So what are all the points that you can reach by taking sequences from the open circle? And then of course you say, oh yeah, this is the closed circle. If you have an open interval, the closure is the closed interval, and so on. Now, what is the closure of the finite discrete measures within the measures? So the answer is these are exactly all the infinite sums where the coefficients are absolutely convergent. So maybe I'm jumping to definition 3. You can even take it as a definition. What is a bounded discrete measure? It's just, you can define it in this way, it's just the infinite sum, but with finite total mass. And because every such thing can be represented again in the natural fashion, meaning with coefficients which are only one, with points appearing only once, then you can have a unique representation. That's exactly the norm. So it's kind of clear, well, if you take limits of finite sums, then you will get an infinite sum. The problem is, however, why it's not completely obvious is, look at the definition of the closure. You're allowed to take one set of coefficients or points for one point, then you take another collection of points with more coefficients, with different coefficients, and so you are having kind of two principles. One is this freedom of choice of those points, which appears to be annoying. On the other hand, the convergence should be in the very strong sense. So you've seen, you're not getting a limit of Dirac measures by the norm convergence. So that's actually helping us out. Intuitively, you can say, well, all the points that appear in this sequence have to have a chance to appear in the limit, and no other point, except, no other point can appear in the limit point. So the principle, which I indicate only roughly here, is the following. If you're in a linear space which has a norm, now our definition of bounded measures was, you take all the linear functionals and you have the functional norm. And actually this is a Banach space. So later on at some time, or as an exercise, we can discuss it. But I think it's very plausible, and you can trust me that this is a valid statement. But the interesting fact is then, if you have now a subspace, which is in our case the set of linear combinations of finite measures, of the linear combinations of discrete measures. So I'm talking about the set of finite discrete measures. Sum of two such finite discrete measures is of course finite discrete, and so on, so this is no problem. Then the claim is that this is exactly the same as the absolutely convergent series in this, so I call it absolutely convergent sums with elements from this subspace. And absolutely convergence means that you have the elements that you're taking from your subspace. So in our case, you could take either the Diracs or the finite discrete measures, but then you are summing up the size of the norm. So it sounds like a harmless statement that a sequence in a Banach space which is absolutely convergent is also convergent, but it's not so completely trivial. Just to tell you a story. You all know that the harmonic series is divergent. The harmonic series is 1 over n, so 1/2 plus 1/3 plus 1/4 and so on is divergent. Easy argument, well, if you take 1/3 plus 1 over 4, there are two guys together, at least 2 times 1 over 4 is 1/2. If you have summed up, I don't know, up to 16, you're saying now I'm taking 1 over 17, 18, 19, up to 32. Then you have 16 terms which have at least the size of 1 over 32. So it's a dyadic block in the harmonic series, and it always adds up to 1/2. So if you take as many blocks as you need, you can exceed any number, so this is clearly not convergent. On the other hand, you also know that the alternating harmonic series, 1/2 minus 1/3 plus 1/4 minus 1 over 5 and so on, is nicely convergent. So you're going a jump to the right, to the left, and always make your step width a little bit smaller, so clearly it's getting more and more narrow and will be convergent. So if you're in Rn, just take the plane and somebody is giving you a collection of vectors. I mean, they might go into different directions, and then it's nice to know that if the total length is finite, that's the condition of absolute convergence, then the sum, independent of whatever the directions are, will be convergent. So in a Banach space, one can prove that every absolutely convergent series is also convergent, and convergence of course means I'm taking partial sums, any partial sum with 500, 501, 3 million, 20 million terms, but one after one, and they approach a certain limit, and that's what you call the sum over all these coefficients. And now the claim of the lemma is whatever element you have which can be approximated by finite discrete measures, you also can write it as a sum. And I indicate here only the argument, and the idea is, well, if somebody is giving you an element x, I'm going in the middle of the proof, which is a limit of elements from the subspace, then of course you can figure out, because it's convergent to this element x, and you must say, we don't know a priori if x is in the space. The interesting case is it's not in the subspace. It's not a finite discrete measure, but it can be arbitrarily well approximated. So you're saying, well, if I wait long enough, I find for the number, let's say 1 over 16, I find one element which is closer by 2, in the norm of the measures by 1 over 16, and I keep that label. Now, behind that element with an even larger index, you find another which is 1 over 32, 1 over 64, and so on. So for each k, you can find an index, and you can choose this index in increasing order such that everything is fine. And then the trick is that you're writing a telescopic sum of these terms. So you're adding up the differences of them. So you compute the differences, because the sum of the differences, because it's a telescopic sum, if you add such terms, you're starting with v1. You add v2 minus v1. You add v3 minus v2, and so on. And if you do 20 of these terms, you're ending up with v1. Pairwise, they are canceling up to v21. So it's just the sum of these terms, sorry, it would be v21 minus v1. And so you're writing the element x as x maybe minus y1 or so, but this is easy to move to the other side. You write it as element from this limit, and you get this representation. So I think it's plausible, and I'm recalling this definition number 13, that the discrete measure are going to the closure of the finite discrete measures are the bounded discrete measures, because we are doing the limit in the space of bounded linear functionals, bounded measures in the measure theoretic sense, and we're getting exactly this representation. And this, in a way, will be dense, but not in the norm sense, because, you know, if it would be dense, you would be able to approximate every measure by these things, which would mean that you can write every measure as a discrete measure. Just maybe to recall it in the course note, I think I have it as a note. If you think of probability theory, you would say that you can make the ck positive, and the total mass is 1. So you would say, well, I have 20 possibilities, and with ck being the probability of hitting the value tk. And then you would say, well, what is the probability distribution function? And that's an increasing function, which is a step function. And the step function has jumps of size ck exactly at these positions. So it's clear that general probability measures are not step functions. So think of normal distributions or so. It's an increasing function, which you all know. And then therefore we have to discuss in some detail the convergence. One of the convergence schemes which I want to just mention at the moment is so-called Bernoulli convergence. So this term comes from probability. So a bounded measure mu0 is the limit of a sequence of measures if whenever you apply these bounded measures to any bounded continuous functions. And we have not done this. We will see that this is possible. You can always extend the action of a bounded linear functional on C0 to CB, but that's a separate thing. So at the moment, I just establish terminology because it's adjacent in the lecture notes. We say it's Bernoulli convergent if for every bounded continuous function you have this convergence. I think it's a good point to take a short break, and I would suggest to take maybe a 6-minute break, yeah, or maybe maybe we restart a little bit before 9:15. Yeah, maybe, yeah. Let's do a 6-minute break. I hope I will be ready by that time. Feel free to write a comment in the chat if you have anything to ask at the moment. I will stop, take a break in the recording here. So I will continue the second part with preparing material and facts about this space of linear functionals, which have been called the bounded measures. And it's the so-called Rees representation theorem, which you can find in books on functional analysis or on measure theory, which allows you to realize that I'm really talking about the same object, but I'm doing it a completely different approach. So I'm avoiding measure theory and still talk about measures. That's, I would say, the difference between integration theory and measure theory. So measure theory takes its pride in saying, we know how to measure sets, therefore we know how to integrate measurable step functions, which means like ordinary step functions, but over domains which are constant, which are more nasty than ordinary boxes or so. So just think of how can you measure the volume of a mountain described by contour lines, and the answer is make the contour lines fine enough, then measure the areas where you are between two such contour lines using Lebesgue measure, and then you're taking limits and you prove that this is all meaningful and that you get the Banach space of integrable functions. We will build L1 from the bounded continuous functions, so the nice easy test functions within M of B. So we will take limits in the same way as we take limits of discrete measures from finite to infinite discrete measures. We will do it and we'll get exactly the same space, but in a more elegant way. On the way there, we need various definitions and harmless terms. The first term, and now I'm really following the lecture notes, but not in exactly the order as they are. I think I will rearrange the order, but not now because that may disturb you, is I use the definition of what is the multiplication of a measure, so a functional with a test function. Actually, not even a test function, it can be a test function, but it can be a bounded continuous function. All actually may be needed for pure frequencies as multipliers or so. Now, in order to make it easy to memorize, we all think that multiplication is commutative, and in a way this is true, but I prefer to write a multiplication of a measure by h to the right and pretend as if it was an associativity law, and in reality it's just an adjointness relation, but it doesn't matter. I'm saying in order to know what mu multiplied with h is on a given test function f from C0, you have to multiply the test function f with the bounded continuous function h. And then, of course, you know that this is in C0, so it's legitimate to apply the linear functional. And then the harmless lemma is, in this situation, the resulting new measure, which I call mu multiplied with h, and later on I will omit the point, is a bounded measure, and the size of the new measure is at most the size of the function h by which you multiply, which is the sup norm, times the size of the functional that you have multiplied by h. So just to go through the proof, because it's not written out in detail, first of all, multiplying f first with h is a linear procedure, then applying a linear functional gives you a linear thing. If you're asking what is the size of this, then you would say, okay, clearly I can estimate the action of mu on h times f by the action of mu, the size of mu, times the size of h times f. And so it's harmless task to find out, but how big is a product function? At most, as big as h with f. And recall, I have shown that a bounded continuous function with a C0 function will be C0, so it will vanish, so everything is fine. And the amplification of the measure by multiplying it with h is at most the size of h. So a very nice situation. Later on, we will use the word Banach module, but so h is from an algebra, so you have internal multiplication. h1 with h2 can be multiplied. The size of h1 times h2 is at most h1 times size h2. And so therefore, what we have here is the first step in this direction, but I don't want to use too much terminology at the same time. Okay, there's also, you can ask, is it always equal maybe? And the answer is no. You can have a function which is fairly big, but so the product is much smaller than this here. Can you improve it? So can you have an estimate like this, which is valid for all the functions h and all the measures mu? Then the answer is no, you cannot improve it in this sense, in this universal sense, but for individual situation you can do it. Now, I'm not sure where I put it, and therefore I have to do it without showing you the text or so. You can ask, or I would say it's a very good exercise also, to say, well, now you're giving me some bounded function. And if you have a bounded function and you multiply with a Dirac measure, you know these are the easiest measures that we have. What can you say about the product? And the answer is, well, the Dirac measure is concentrated at a given point. So maybe we take the Dirac measure at 0. What happens if you multiply a Dirac measure at 0 with h? Well, maybe just look at the definition. You have to apply the evaluation mapping to the function h of 0 times h times f at 0. Oh, what's the product function at a value of 0? It's by definition of how do you multiply a function. It's h of 0 times f of 0. So what are you getting? You're getting a multiple. The scalar multiple is h of 0 times the value of f at 0. So it's h0 times delta at 0. So in words, it's easier to formulate it in words here. If you multiply a Dirac measure with a function, you get exactly the value of the function which is multiplying h of the position times the delta at this position. Adding up with finite measures or taking even limits, you can multiply a discrete measure with a bounded continuous function. The resulting measure will be a sum of Dirac measures with the modified amplitudes by h of xk. So this is really what you're getting. Okay, the next thing I would like to use or introduce is a notion which, at least the terminology, is something that I have introduced many years ago, and it has become quite popular. It's an abbreviation. It's the word BUPU. A BUPU is a bounded uniform partition of unity. And I will use mostly the regular case, which is that I'm using shifted functions which add up to 1. And these shifted functions are coming from bump functions which are constant which have compact support. So the boundedness refers to the boundedness in terms of the action on some space. We will, in the moment, you can think of psi to be a function with values between 0 and 1. So non-negative functions between 0 and 1 are the most important things. So it's just boundedness in the subnorm sense. So they are all equal size. If you shift the psi, it's bounded in the sense of boundedness over all the positions. Important is the finite overlap property that I assume. So I have a lattice, and I will show pictures in a moment. Therefore, this sum, even if it's formally an infinite sum for every given argument x, only finitely many of them are overlapping. And the partition of unity is that you're decomposing constant 1, which is kind of the unit element, of course, for pointwise multiplication, into pieces which are all supported. in a more general situation on groups, you can do it in the same way. I don't do it here. Just maybe here the comment. The finite overlapping property is the important thing. And if I would give you a non-regular partition of unity, I would say it's something that on the one-dimensional case looks like this. So you have functions which are kind of not overlapping too much. Maybe in this kind, every individual term, maybe you take a red one, it's overlapping with, let's say, 2 neighbors to the left and 2 to the right. But the size of each of these supports is also quite limited or so. And you can imagine that if you are in multi-dimension, you're having products of such objects and you're getting fine bupus. And the best way in the Euclidean setting, which we have for this course, is you take any partition of this kind and compress it. I've put into the extra file, which you can download more beautiful pictures. And you can dilate these things. So kind of playing harmonica of such a partition of unity will give you a fine partition of unity. And we will use such things to produce a lot of functions or modify measures or so. So this will be a very harmless but very useful tool. I would say one of the underestimated tools, because partitions of unity appear in mathematics in many places, mostly in differential geometry, I would say, where you're saying, well, a smooth surface in R3 is locally almost like a collection of patches. Each of them is 2-dimensional. And so whenever you're trying to study in a local coordinate system, a smooth surface in R2, you would use a decomposition of the surface into local pieces. Locally, everything is like Euclidean spaces, so everything is planar in that case. And therefore, everything that you can do for functions on R2 can be transferred, not everything, but the interesting differential geometric properties of functions on the plane, on the flat space, can be transferred to slightly curved pieces. If you make a partition fine enough, you get all these things. And okay, also there it's important. If a function is smooth, meaning in differential geometry very often infinitely differentiable, then if all the pieces are smooth, so that's why you have to have partitions of unity which have a good quality in terms of smoothness. We will later use it for time frequency localization, so we should not introduce kind of jumps or nasty corners in the partition of unity, and still localize. So that will be also the starting point for time frequency analysis. So actually, if you look at the STX software, what people are doing there is they use more or less a partition of unity, which is regular, which is kind of continuously going in that direction. And so everything is fine. Now, the claim that we have here is that if you are giving me any such partition of unity, then, so it's theorem 4, which I want to discuss next. If you give me a bounded measure, so such a functional, then you can decompose it into the pieces. So it's kind of a local action. And this local action have a total measure which is exactly the same as the measure of the original function. So this will be a very important tool for the discussion that we are having ahead of us. And of course, if this is true, it means that if you're giving me a bounded measure, then it has to have an absolutely convergent representation of measures, where you would say, and that's a good intuition, that all these pieces are now measures which act only very locally. I mean, just remember, if you take mu psi I and you apply it to any function f, maybe you try to apply it to a chirp function, what you're really doing is you're localizing the argument, so you're multiplying the chirp function with the psi I, so you have a piece of a chirp function, and then you apply the functional. So it's kind of One can argue that we will define a support of a functional later on, and the support of mu psi I is just inside of the support of psi I. Okay, so why is this possible and why is it relevant? So maybe first the argument, if somebody explains to you measure theory, then you're having an important property called the sigma additivity. So if somebody is taking finitely many measurable sets which are disjoint, kind of think of the area in the plane, you have blobs which are, sets which are disjoint, then you would say the total measure of this is the same as the sum of the measures. But this is not only true, that's the trick of Lebesgue's measure for finite linear combinations, but also for infinite linear combinations. So really in the sense that if you give me infinitely many measurable sets, which are disjoint, either they are having total measure plus infinity, or they have a total measure which is finite, and then of course this measure of this infinite countable union of sets is the same as the sum of the measures. So that's so important for measure theory, and I would say that theorem 4 is exactly the analog which is resulting from the good properties of a dual space, of a space of linear functionals on any Banach space. In our case, bounded measures are dual of C0. So C0 is a nice space, and we will see, I will give you only an outline of the proof in words, so to say, that this harmless nice space C0 and some of its properties allow you to prove this very strong property 52 of the bounded measures. So the first statement is very harmless. It's just the completeness of the space of linear functional, which I may discuss later on. It's clear that if you're having a situation where somebody is telling you, I have a bounded measure, and the countable many pieces are giving you an absolutely convergent thing, then of course the sequence will be convergent, and it is very harmless to see that, well, the action of that sum on a test function f is of course the same as mu, the sum of mu applied to psi if. But the sum of the psi is 1, so the sum of the mu of psi if is just mu times 1 times f, which is mu of f. So this estimate is just the triangle inequality plus the completeness of the bounded estimate. So the difficult part is to show that it cannot be smaller, it's exactly this. Now, I'm not sure, maybe I have to make it a little bit smaller. I hope you can still read it. I will try to give you the idea. The first observation is, just recall again, what is the norm of a functional? I can make it still bigger. A functional is the sup over the input. So if we want to get an estimate from below, we can say for every epsilon and for every measure, there exists a function f such that the size of f is less than 1. Typically, it will be equal to 1. But that the output is in terms of size. Okay, we have to show that if we reduce this number, our target number, by epsilon, and it's more convenient to say 3 epsilon, we will find such a function. Now, I have here even put a function with compact support because compactly supported functions are inside C0. Okay, now I like to play the role game. You're challenging me to solve this task. So you're giving me a very nasty tiny epsilon, and I have to use this information. You're giving me the mu and the epsilon, and I have to figure out how to produce such an f. Now, the first thing is to say, well, if you give me a finite positive epsilon and countably many numbers, I can produce infinitely many epsilon such that the sum is less than this. We all know that 1/2 plus 1/4 plus 1/8, so power of 2 to the minus k is adding up to 1. So maybe I take epsilon 1/2, epsilon 1/4, and make an infinite sequence out of this. Because we will look at these mu psi I, at the pieces of the measure individually. Okay, and so for each such new measure, we apply the definition of the lower bound. We can find a function f with label I, which has norm 1. I would say we can take it from the dense subspace of continuous function with compact support. Maybe I have to correct this, or at least. But let's see. And that function reacts very strongly on this. So mu psi I is showing strong output. But what is mu psi I? It's mu times the localized version of fi. And you're getting the norm of this local measure minus epsilon over I. Okay, now we can assume that these numbers, which in my situation might be even complex valued or real valued, are non-negative. Why? Because assume you're having a real situation and you're getting a negative value, then just by changing fi to minus fi, you get a positive number. Or if it's complex, you take the argument of this complex number and you get a positive number. This is convenient because it allows you to avoid addition of complex numbers, which may cancel out and add up to 0, even if all of them are harmless. Now, what we will do in order to come up with a continuous function is we will choose a suitable finite set. So I would say we collect the important elements for the sum, such that a finite sum of these elements, fi times psi I, is giving us a significant output to the measure mu. Okay, so how do we choose the finite set? Okay, maybe the first argument should be, well, whatever finite set we will choose and whatever we fabricate new functions from this collection of f1, f2, f3, and so, if we glue them together with the help of the partition of unity, that's the line in here between, what is of this f, what can we say about the size of the f? And of course you would say, okay, f of t is the sum of fi of t times psi I of t. What do you know about the fi of t? It's just at most the size of the fi. But each of the fi's, the individual functions, were having size 1. So at the end, you're ending up, oh, I can estimate the value of this new function f independent of how big my finite set is by 1 times the sum of the psi I. Because I was choosing the partition of unity non-negative, this is 1. So I can fabricate a lot of those functions. All of them are candidates because the support of this new function f is compact because all the psi are living on some, let's say, intervals in the one-dimensional case. Now, the next thing is, in order to help us to find an appropriate finite set is, well, we remember that mu is a linear functional. So if we take mu of f and we apply it to finite sum of the form psi I of f, it's just mu individually applied to these things. So instead of, once more, mu applied to a finite sum of the form psi I f is the same as the sum of the linear functionals. So it's the linearity which takes the first step. Now we take the definition. Well, that's actually the same. So yeah, maybe here I should write mu psi I of fi. So I've not moved this over. But the choice, so now it's an individual consideration. For each I that we have under consideration, we have chosen the f with the corresponding number in such a way that you're able to get mu psi I, the norm, minus epsilon I. Now, it's a finite sum, so you're separately summing up over the terms of the over the mu psi I measure norm. and the sum of the epsilon, and you have seen that they are at most epsilon. So we are just observing that, well, if this sum is absolutely convergent of these pieces, so this sum of positive numbers is finite, then we can choose a finite set such that whenever you choose all those elements from F0, you will have a very good approximation, or the rest will be smaller than epsilon. So if I go back, I will say, well, you have given me the epsilon, and I'm choosing a finite set, maybe F0 or a larger set, such that this estimate is giving me the mu psi minus epsilon, and this is what we had to prove. Okay, important message to go back to the theorem. You can decompose every measure by any partition of unity of this particular form into pieces. Each of the pieces is a linear functional. It can be measured in the measure norm, but the sum of the pieces is exactly the measure norm. So in measure theory, probably you would say, okay, he can decompose a bounded measure on the real line by taking indicator function from the interval from n to n plus 1. So you localize and take the measure mu n, which is the measure of a set intersected with the half-open interval from n to n plus 1. And clearly, these pieces are giving together are the real line, and therefore it's the sigma additivity for these concrete measures. In my case, I'm not allowing discontinuous partitions of unity, also they are quite nice, and therefore I have to make continuous partitions of unity, which have to have some overlap, otherwise I cannot get constant 1, and that's why I have to be a little bit more careful with my argumentation. But you see, I don't have to introduce sigma algebra, sigma additivity. I get this crucial property for free. Now, in words, very harmless statement is, whenever you have an absolutely convergent series, it's also convergent. And now I would like to introduce a concept of convergence, which is a little bit more general than the concept of convergence as you know it for sequences or ordinary series. Normally, you would say, instead of writing I in the countable index set I, you would probably write summation over n in the integers or in natural numbers. So you'd say, okay, what is a series? You are taking the first, the second, the third element, and to say the series is convergent is saying all the partial sum from 1 to sufficiently large k are close to the limit. So you have a clearly ordered system of partial sums. You are having short and long and very long partial sums, and they are an increasing sequence. Now, we are dealing with a multidimensional situations. So even if you take a regular BUPU, the index set, the full index set might be the two-dimensional lattice. So if or even in the one-dimensional case, I mean, you're taking the integers. How would you sum over the integers? You cannot start, well, symbolically, you can start from minus infinity to plus infinity. But if you really do a counting of the integers, you can only do it in some order. You can say, okay, I'm starting with 0, plus 1, minus 1, plus 2, minus 2. Or you're starting from 0 until 100. And then you say, now I have to take some negative 1. And then I go from minus 1 to minus 200 and so on. But there's so many ways to do it. And the much better way of looking at this is to say, well, I can look at these countably many terms, which I put into a bucket, so to say, and each time I pull out, I get a finite sum. And of course, convergence means, well, there are only finitely many which are really relevant. And if I take more, it's fine, but it's not really much better. So convergence over a countable set is even uncountable, but here I think of countable is valid if you have the following situation. You're giving me an epsilon, so the claim is I have an unconditional convergent in the sense of this net of finite sets is convergent to the infinite sum. So what does it mean? It means if you're giving me, I have found a measure mu, and it has the property that we are getting close to these partial sums. So maybe I should write mu times psi I here actually. It will be close, I mean, difference will be small whenever the set is close enough to the full set. What does it mean? Well, it's comprehensive enough. So if there is a finite set, one of these elements in this collection, that everything which is more comprehensive, better than this finite set, it can be equal or so, is giving you a good approximation. So, I mean, it's like ordering in a shop and you're saying, this is my shopping list. And I'm satisfied with the delivery service if I'm getting those 20 things which I have on my wish list. I think nobody would mind if you're getting for free some extra items. And so everything is good enough in the spirit of good approximation in our case, if it has all the relevant terms. But if you add more, it should not get worse. So you shouldn't have any negative items in your pocket. So all the rest will be small. This is then the term of unconditional convergence. And we have this situation. Now, I will use, and I think it's good for you to see it today, and then we will go back with these partitions of unity later on. Also with the term of a discretization, spline approximation operator. So definition 18 is using now these partitions of unity not at the level of measures, but at the level of functions. So the terminology I will use is I call SP psi. So psi is such a partition of unity, a bupu. I call it a spline approximation operator, a spline type operator, or a quasi-interpolation operator. I'm not sure completely whether I don't want to move things too much, but the term quasi-interpolation is, of course, a generalization of the term interpolation operator. So maybe you know how MATLAB is plotting a data vector. So if you're looking at a data vector, you're not getting, you have two choices. You are using the stem command, then you will see those needles that we have seen at the beginning of today's session. Or you're saying plot in the ordinary way, and then we'll do a piecewise linear continuation between the points. So if I say plot the function which has values at a given set of points, usually a linear progression, arithmetic progression, and the data are the sampling values f of xi, then it would do a piecewise linear interpolation. Now, my interpretation here, and this I will show you more examples later on, will be, well, this is a piecewise linear interpolation operator, so something that MATLAB is actually doing automatically without much discussion. I view it as a partition of unity psi I, which consists of triangular function. So triangular function, clearly, if you make them from point, let's say, what is the psi I at point number 5? Well, it will be a triangular function starting at point number 4 and having a peak at point number 5 and going down for point number 6. So if you take a collection of triangular function built in this way, it will be adding up to 1. Every guy will overlap only with the immediate neighbor, so it will be a typical partition of unity. And what are you getting if you add up those triangular functions? You will get a function which is a sum, a finite sum of linear functions at each point. I mean, affine functions would be more correct. So it will be a straight line. What is the value at each of the peak node points? It will be f of x3, x5, x4, x5, and so on. So it will be exactly the piecewise linear interpolation operator. So the most important special case to understand why this is a useful thing is do this quasi-interpolation and do this thing. If you would do higher order smoothness, so in order of using local linear pieces, you would take locally quadratic or cubic polynomials, and then essentially one way to understand numerical integration rules is that, well, we are doing a kind of analytic integration of those piecewise polynomials, and then we just insert the values of the function. And so the integration rules that are kind of sold to you by people in numerical analysis are exactly the arguments that you say, well, I cannot integrate f, it's too cumbersome, but I can approximate it by a quasi-interpolation or interpolation of some form, where the psi-i's are integrated already by the standard rule of integrating polynomials without really doing this Riemannian sum business. And then we're doing linear combinations, and that's how these integration rules appear. Okay, so you can imagine that that's the next step I would like to take at the end of this session now, is to give you an idea that if you're taking a piecewise linear interpolation with a fine grid, then the resulting piecewise linear interpolation is very close to the original function. I mean, I'm using this, for example, in order to plot a circle with MATLAB. Whenever you want to plot a circle, what I'm really doing is I'm plotting the unit roots, let's say, of order 360, and MATLAB is plotting in the complex curve, and it's showing you a nice circle. Or if you are not satisfied, take a larger number. The only thing you have to connect the last value with the first value. So I'm taking unit roots of order n, add at the end a 1, and then I plot this in the and you don't see a difference between the continuous circle and the piecewise linear object if everything is fine enough. So that's about the idea that we would have. So what is the statement? The operators psi, which at the end are all non-expansive. So this new function doesn't have a chance to be larger than the original function. So the pointwise values, it cannot overshoot the original values. And the more delicate property is these piecewise linear interpolations or quasi-interpolations of continuous functions will give you continuous functions. They will map C0 into C0 and bounded continuous functions into bounded continuous functions. And moreover, and that's why this uniform continuity is so useful also, if the function is uniformly bounded and continuous, then the spline approximations will converge to the function f whenever the size of the diameter is going to 0. Okay, so we have to prove this, or at least find an argument why this is highly plausible. Now, the key estimate is actually a pointwise estimate. So imagine that somebody is giving you such a function, okay, sorry, it's turned into a g now, such a uniformly continuous function g, and you would like to see whether it's small. So kind of what you would have to view is look at an epsilon strip around the original function and check whether the piecewise linear interpolation is really close enough to the g when you do this. Then you have a good intuition about what's happening. And the claim is, well, you have to look at the local oscillation. Now there are two possible definitions of what is the delta oscillation of g at a point x. The maybe more natural one would be to say, well, the oscillation is the biggest difference. So it's if you take real valued functions, it's the difference between the biggest and the smallest value. But even in MATLAB, when you would compute it for maybe a complex valued function, you're looking only at delta neighborhood would be, I don't know, 7 samples to the left, 7 to the right. So you would look at 15 samples and look at the biggest difference of pairs of 15 numbers. You would have to compute absolute value of 225, 15 squared complex numbers. So it's more reasonable to take the oscillation as deviation from the value at the center. So you're looking at small h, delta neighborhood of h, and you're looking at the maximal deviation. So in this size, and if you're moving around the graph of your function in the delta neighborhood, and you're asking, what is the worst deviation in this small area of a circle of radius delta from the central value at x? So you get a new function. It's nice to prove, but very plausible, that this is a continuous function. And what we have to estimate is first to say, well, if the size of our partition of unity is delta, so we have already a very fine piecewise linear interpolation, we can estimate it pointwise by this oscillation function. So there are two tasks: find the estimate 55 and then prove that this oscillation goes to 0 as if you take a uniformly continuous function. Now, the first term is the pointwise estimate. So what is SP psi of G minus G? And we have two facts. The sum of the psi I is constant 1. So what you're doing is, to get to the right-hand side, you just write G as G times 1. But G times 1 is the sum of the psi I times G. So what is the difference between the term that you have in the spline approximation theory? It's psi I of x times G of x, whereas in the interpolation term, it's G at the center. So we have to estimate in the pointwise sense everything at every position, wherever you look at it. Only finitely many psi r's are involved, so this infinite sum is only a formal infinite sum. You have to estimate this difference. And of course, you should try to do this by yourself. It's a little bit compressed representation, but it's actually what you do. But because for fixed I, it's finitely, I mean, for each individual I, you only have to look at psi of x times this. So you don't have to look at all the possible argument x which are floating around, but only those where the psi of x is different from 0. But the psi I of x is concentrated near the point xi, and the psi I all have small support. So by the assumption of smallness or fineness of the partition, so if you have a delta partition of unity, only the differences between two arguments xi and xr are coming in. Now, of course, in the way how you construct it, you put these psi i's at different places. Therefore, you would expect that you have to look at the oscillation from the point of view of xi. But then we would get samples of the oscillation. That was actually my original approach. But then I realized with this moving oscillation, I can say, no, I'm not far away. This only is relative. The summation is non-zero only if the xi is near x. So we have a continuous oscillation term here at x. And because psi I is positive in our choice, we can put psi I of x. Okay, so we get an estimate at each point. Only finitely many psi i's are involved. Once you look at individual psi I, you know that they are taking influence only from a little bit away, and you have oscillation of G at the point x. So I like to write this in an pointwise sense, and write that the function, the difference between the spline interpolation operator applied to G minus G, this is a function, and in absolute terms, it's not more than the, by definition, non-negative function, which is the oscillation function. Now, the next thing I'm saying here, the proof is finished, but I have to add one argument, of course. Now, because the function g or f in my statement is supposed to be uniformly continuous, we know that if you give me an epsilon, I find a delta such that whatever the argument differences are, as long as the positions are closer than delta, the difference will be smaller. So in our case, we want to estimate the sup norm, and that's a very easy task now. If you dominate a continuous bounded function, both of them are bounded, continuous bounded, then you will estimate the sup by the sup of the larger one, and that is going to 0 by the definition of uniform continuity of the argument g, and that's how we prove this. It's not stated here, only in the lemma, and that's why I can give this as an assignment to prove that the boundedness is preserved, so the size of the new function sp psi of g will be also at most this, and that if the function g or f is decaying at infinity, it's clear that the same is true for the sp psi operator. Maybe that's a little bit more cumbersome, but if you think of the case of piecewise linear function, it's quite clear what you're doing. You're saying, I'm going into an area where all these samples are, which are not used, are less than epsilon. So I'm going outside of the ball or circle of radius r. Then all the ingredients that are built from the difference. So of course, maybe I should remember or recall the difference between f located to some bounded set and the spline approximation means that you're having only values which are from far away from the center. So I'm using only for the tails of this difference, I'm using the small sampling values of f near infinity. They're all uniformly small by the definition of what C0 means. And therefore, your mapping sp psi is a linear operator which goes to 0. And we have a nice observation that you would say, well, what do I look for? I'm looking at the difference between the spline approximation operator and the identity operator. So it's just a difference of two operators. But now we are in a situation very similar to these measures. The operator norm of sp psi minus f identity is not going to 0. If I'm claiming that, well, for some very fine partition of unity, everything is fine, you easily come up with a very nasty function which isn't C0 and which has norm 1 where the difference is 2. So that's not uniformly. But once you tell me, I have a given function, can you tell me what happens when you apply your operators to the f, and you compare to the action of the identity operator, then you have convergence. So in the terminology of functional analysis, which we will use later on, but slowly, is the operators are tending in the strong operator topology to the identity operator. But this is just a mathematical formulation for the statement that you have in lemma 17. That means whenever you have a fixed input, you have convergence. And the convergence is now, again, not in the sense, there's not a sequence or so, but it says, whenever you have good quality, the approximation will be a good approximation. So it is only in terms of the size, and you can imagine when there are infinitely many or uncountably many partitions of unity which are all fine enough, and it's more in the spirit of Riemannian sum, where you also say a function is Riemann integrable if any Riemannian sum which is fine enough is close enough to some number, and that number is called the Riemann integral. I think I will stop here, and I will also stop the recording, and thank you very much for your attention.